up until this point in the semester, everything we have learned is 19th century physics. It was all done in the 1800s, which is wild. But it is by no means new material in the in terms of human history. That's one reason why I think it's ridiculous that some instructors ask you to pay $150 for an intro physics textbook. It's information that is literally a century and a half out of date. So you should get that for free, which is why we use the OpenStax book in this class. But today, we are actually taking our first baby steps into the 20th century. Now, it's not a very big step. It's actually just 1905, so don't get too excited. In 1905, Albert Einstein published 4 papers that in 3 different fields that revolutionized each of the fields that he published in. It's relatively pretty big. Okay, so it's going to be that kind of day. The papers that he published were on the photoelectric effect, which we are actually going to study later in the semester. He published on Brownian motion, which was an explanation for why very small particles appear to move back and forth as if they were alive. He published on the equivalence of mass and energy. It's where his famous E equals mc squared expression comes from. And lastly, he published on special relativity. That's what we're going to tackle today. That year was so revolutionary that at the time, and still today in some texts, it's referred to as the Annus Mirabilis, the Year of Miracles. All right. To begin with, we need to talk about what a reference frame is. So, if you took, again, maybe not your particular Gen Phys one, but the way I teach it, one of the most important things to do is you have to specify your coordinate system. So you know where height is 0, you know which direction is positive, which direction is negative. If there's a tilt, if you've got like a box on a ramp problem, it's important to put that in there. And so defining your coordinate system is a really important step of solving physics problems. The fancy term for defining your coordinates when physicists are feeling fancy, we say that we specify a reference frame. In other words, we are defining where the origin is, and every other position that we specify is going to be in reference to the origin that we defined. Every speed that we specify is going to be in reference to the origin. And when you went through Gen Phys 1, you may have realized, in fact you should have realized, that you're basically free to define your coordinate system whatever way you want. Right? Some coordinate systems are more convenient than others, but none of them are wrong. Right? You will get the same answer no matter where you put the origin, no matter which direction you say the x-axis is, right? So if we have something like a box on a ramp, right? And this usually happens pretty early in GenPhys 1. You can do this problem by saying, oh yeah, x is to the right and y is up. And there's some weight going on. There's normal force. There's some friction, right? And then we write down Newton's second law. Sum of forces equals ma. And if this box is not moving, that means that sum of forces are 0. There's no acceleration. If you do this, then you end up with something like sum of forces in the x direction is equal to f cosine theta minus n sine theta equals 0. And sum of forces in the y direction is equal to n cosine theta plus f sine theta minus mg. And this is a relatively inconvenient way of analyzing this problem. So it's frequent. What we do instead frequently is say, well, actually, let's let the x direction be up the ramp, and the y direction will be in the direction of normal force. So now when we say, what's the sum of forces in the x direction? That is f minus mg sine theta. And the sum of forces in the y direction is n minus mg cos theta. And that's a lot nicer to deal with. Did anyone not have this kind of experience in Phys 1? In 151? Right? Does this accurately describe something you encountered in Physics 151? Okay. Cool. So the kicker, the punchline to this, is that whether you choose your coordinates like in the blue or in the orange, you get exactly the same answer. What we didn't explicitly cover in GenPhys 1 usually is that your coordinate, your origin, does not have to be stationary. It can move. And there are times when that's convenient. If we have a train which is moving to the right, then maybe it makes sense to say the origin is at the front of the train. And yeah, the front of the train is moving, but so is the origin of our coordinate system. Right? And in this coordinate system, the velocity of the train is 0 because it never moves from it never leaves the origin. But the velocity of this tree that the train is about to pass by might be equal to negative 30 meters a second. Did anyone encounter stuff like this last semester? Say no more, Arthur. this moving coordinate system on the train is also perfectly okay. Your coordinate system doesn't have to stand still. However, there is one thing that your coordinate system cannot do. It can't accelerate. And the reason for this is because no matter what coordinate system you choose, everybody in their own coordinate system needs to be able to agree on what forces are being handed around. So with the train example, whether you have your coordinate system moving with the front of the train or you have it stationary with the tree, you might those two coordinate systems will disagree on what the velocity of the train and the velocity of the tree is. But they will still agree on what the net force on the train and the tree is, right? Neither of them will conclude that the other object has a force acting on it, because both of them will see that the constant velocity is a constant velocity, and so there's no net force. So both of these two kinds of reference frames, both of these are inertial reference frames. So reference frames in which, any family of reference frames that all agree on forces, even if they don't agree on velocities, are all inertial reference frames. And as long as your coordinate system isn't accelerating, you're good. This is part of the reason that, for example, we have something called like the Coriolis effect. So the surface of the Earth is not actually an inertial reference frame. It's actually accelerating, right? Because any piece of ground on the Earth is actually rotating in a circle, and if it's moving in a circle, it must be accelerating, right? There must be some centripetal acceleration equal to v squared over r. And it's a small acceleration, right? Because the Earth is big, and it takes a whole day for us to go around one time, right? So our angular speed is only 7.2 times 10 to the minus 5 rads per second. So our centripetal acceleration is not very big, right? It's like a centimeter per second squared. So it's a small fraction of gravity, but it exists. And because of that, we are not quite right if we try and fire a projectile a long distance, or if we try to fly a plane, or anything like that. We actually have to correct for the fact that the ground is accelerating away underneath us, and that's what we call the Coriolis effect. You may or may not have encountered the Coriolis effect in Gen Phys 1. Probably you did not. So the first thing that Einstein said about special relativity is he noted that, hey, actually, if you deal with inertial reference frames, that's the easiest way to write down the laws of physics. Right? The laws of physics are the same everywhere and are in their simplest form if you use inertial reference frames. Right? So if you have non-inertial reference frames, you disagree on forces, which means you disagree on work done, which means you disagree on energies. So yeah, like the laws of physics don't work if you're trying to compare two reference frames, one of which is accelerating with respect to the other. Okay. So that's postulate 1. So inertial reference frames are awesome. Two. When we did our section on electricity and magnetism, one of the side attractions that we got was that the speed of light is equal to 1 over the square root of the permeability times the permittivity of free space. Okay. This is actually the first way we estimated the speed of light. Before we could measure it directly, we could measure the permittivity and permeability, and we knew this relationship. So that gave us our first estimate historically as a species. It gave us our first estimate of the speed of light. Einstein came along and said his postulate was the speed of light is the same everywhere. And right, the source of that light doesn't affect that. This is kind of remarkable. Imagine you were does anyone play chicken in the pool? People know what I'm talking about if I say play chicken, where someone gets on your shoulders and you... Yeah. So... I don't know why I just thought of this, but one of the things that we used to do when I was a kid was we would include water balloons into our games of chicken. So... you have the person on the bottom, someone on their shoulders, and the person on the bottom would charge forward, and you would toss a water balloon at the opposing team. And the reason you charged forward, because if you could build up some speed before you launched the balloon would travel faster. And, there's that little bit of fear factor. You're trying to get other people to dodge your water balloon and fall off the shoulders of their partner. So the faster you're moving before you throw this water balloon, the faster the water balloon is going, right? I mean, that's conservation of momentum from Gen Phys 1. But light doesn't work that way. Let's say that you are sitting in your pickup truck. And you've got the headlights on. The velocity of the light Okay, look, just add pickups to the list of things I can't draw, okay? It's Okay, so the velocity of light is 3 times 10 to the 8 meters a second. Well, what if your truck has a speed of 100 meters a second? Now that's real fast for any land-based um, vehicle. So you pick up amazing speed in your truck. The speed of light, still 3 times 10 to the 8. And that's not just because 3 times 10 to the 8 is a lot bigger than 100 meters a second, and so you lose it as a rounding error. If you um, have a satellite orbiting Earth, um, you all may or may not know that to stay in orbit, an object has to be moving sideways at just incredible velocities. So, in near Earth orbit, around the altitude of the International Space Station, this velocity is. Oh, I don't want to use that color. This velocity is approximately 8,000 meters a second. You know what? That's exactly where I learned about orbital mechanics from. So, yeah. I got a physics degree, and I'm like, yeah, I totally know about orbital mechanics. Then I started playing Kerbal Space Program and realized I didn't know anything about orbital mechanics. But if you shine a laser off of this satellite, speed of light, still 3 times 10 to the 8. No matter how fast the source of the light always moves at the same speed. Right? So that's kind of wild. But that is Einstein's second postulate for special relativity. Okay. So that's section 28.1. 28.2 starts to go into simultaneity and time dilation. If if light always travels at the same speed, no matter the velocity of the source, right? Then one thing that kind of breaks down is our idea of things happening at the same time, and sometimes even things happening in the same order, right? So if we have two events, the order with which we perceive them may actually depend on how fast we are going. And there's a classic example in your book where we imagine that there are two people, one of whom standing on the ground, one of whom's on a train, and there are two lamps that can flash light inside the train. And we imagine what the two observers inside and outside the train would see. Okay. I guess I should ask, has everybody actually read this section, or are there people who have not read it yet? Okay. So if the flashes of light, um, if each lamp, I'm just gonna go ahead and copy this diagram from the book. All right. So this guy in suspenders. By the way, I think suspenders should come back in a big way. They're like way more fashionable than people give them credit for. So if the two lights flash, just as this train car is passing the person outside, then both of these um, light sources, the light travels at the same speed, which means that they will both reach this guy at the same time, which means that observer B here, this dude standing outside the train, will conclude that both lights flashed at the same time. That is not what observer A will observe, right? The one inside the car. So once the light has flashed, it's going to move at the same speed no matter which side it's coming from. But the person inside the train is going to continue moving to the right, which means they will encounter the light from the lamp on the right before the light from the lamp on the left gets to them. So they will conclude that the lamp on the right flashed before the lamp on the left. Does that make sense to everybody, or does everyone have a huge headache after thinking about that? It's a hard thing to wrap our minds around, right? For the light that is traveling to meet observer B, the path length for both of these lights is the same. Since light from both lamps had to travel the same length, the same distance in order to reach the dude in the suspenders, it took the same amount of time for light from both lamps to reach the dude in the suspenders. So the dude in the suspenders sees both flashes at the same time. So in his perception, he sees both of them happening at once. But yeah, for the girl, this distance that the lamp on so light from the lamp on the left has to travel a distance equal to, right, the original distance minus whatever distance the girl has actually traveled in the time it takes for the light to reach her.
Why minus and not plus? Wait, the one on the left?
The one on the right. So for the lamp on the right,
gotcha.
Yeah, since the girl is moving toward the point where that light was emitted from, that light doesn't have to travel as far. But on the other side, the light has to travel further, right? In order for her to perceive it. Anthony asks, so why doesn't Earth's rotation affect that? It totally does. In fact, we have to correct for this all the time. Anytime you have any satellite communications, we have to do a correction for relativity, or else we get the distances completely wrong. So if your GPS did not do a relativistic correction, it would misjudge your altitude by something like 15 meters. Which is bad when you're asking it to give you directions. Okay. This actually gets worse. So, in the train example, is a thought experiment, and Einstein was famous for these thought experiments. Like, imagine what would happen if, right, we had this situation. So the two observers disagree on whether the two flashes happened at the same time or at different times. A more extreme example, where we have someone moving at orbital speeds in a space shuttle versus someone who is observing on Earth's surface. Here's the experiment, right? So the space shuttle is moving to the right. It's orbiting the Earth. And in the vertical direction, we're doing an experiment with a laser. Right? So the laser, I should use a different color. The laser is emitted from, like a laser pointer. It doesn't have to be too expensive. There is a mirror that the laser bounces off of. And then there is a detector right next to the emitter. So the laser comes out of the laser pointer, bounces off the mirror, hits the detector. These two, like the emitter and the detector, are so close together that the distance in the horizontal direction is just negligible compared to how far apart they are from the mirror. So if they are a distance d from the mirror, then the astronaut says, oh, light traveled a distance of 2d. Right? Thank the experiment, let's go home. But the observer on Earth, maybe someone in NASA's control room, is like, hey, wait a minute. Wait a minute. Light traveled way more than 2d because you were going fast to the right. Right? So we have to actually use, the Pythagorean theorem here. From the perspective of someone on the ground, the light didn't just bounce up and come down. It was going at an angle because the space shuttle itself was going, like 1% the speed of light in the orbital direction. or I guess a few percent the speed of light in the orbital direction. So light has to go bounce off the mirror. And of course, the mirror is also moving horizontally at that speed. Right? Bounces off the mirror and comes back. So this distance that we've traveled in the horizontal direction is no longer negligible. It's significant. And so the observer on Earth concludes, actually, we need to use the Pythagorean theorem. That horizontal length can't be neglected. And so your total distance is equal to square root of d squared plus L squared. Now here's the kicker. Both of them agree on what the speed of light is. Okay. Speed of light, S here is a distance. Both of them agree that the speed of light has the same number. But the astronaut is going to say that that is equal to 2d divided by the amount of time that it took for the laser to bounce off the mirror and come back. The person at NASA who's observing is actually going to say, well, no, wait a minute. That's going to be 2 times this diagonal distance that the light traveled divided by the time it took to make that journey. But D and S are not the same. So they don't agree on how much time has passed. They don't agree on how long the experiment took. Right? And there's a full full derivation in your in the textbook. But the kicker at the end is they are going to disagree by a factor of gamma. Nicholas, it turns out they're not going to agree on time and they won't agree on length. They will disagree on both of those things. So the time that was measured by NASA is going to be equal to this gamma factor times the time measured by the astronaut. Right? So they will disagree on how long the experiment took. And because they disagree on how fast time is going, they're actually going to disagree on how long things are, like distance-wise, right? Which is in 28.3. So for exactly the same reasons, we have this same factor of gamma pop up again. So if you're trying to measure lengths in the direction that you are traveling, right? So let's say the astronaut was trying to measure how how far the shuttle moved during the time this experiment was happening, right? But NASA and the astronaut, they disagree on how long the experiment took. And so they will disagree on how far the shuttle went. So NASA will say that the shuttle traveled one distance. And the astronaut will say they traveled a different distance. And they will be different by a factor of gamma. Yeah, that's not an accident. So the movie Interstellar is, it has its problems. It definitely has its problems. But they did hire a physicist to make sure that they got at least some of the science correct, including the relativistic effects. Granted, they threw away all of that science in the last act of the movie and introduced something completely ridiculous, but at least the first 2/3 of the movie are relatively okay from a science perspective. Alright. This actually seems like a good point to take a break. Let everybody digest this for a minute. And then when we come back, we will talk about how these two things, the disagreement on about time and length, we will talk about how this affects our measurement of velocity, momentum, and energy. So my clock right now shows 12:41. Let's take a 10-minute break. Be back here at 12:51.
This video is sponsored by Wondrium. Stay tuned to the end to find out more.
Imagine, if you will, that you have a very powerful laser pointer on a clear night and you point it to the... And how would causality be broken if information would travel faster than light? What would that mean for the universe? The fascinating story is coming up right in the electromagnetic field. This is why it exerts a force. Light pressure is one way that electromagnetic fields exert a force on an object. The speed of light is the speed at which the disturbance of the electromagnetic field can propagate. So in summary, the speed of information is the speed of a force field. You can't send information faster than the force field can change. There has to be a disturbance in a force field for any communication or causation to occur. Light in a vacuum travels at c, the maximum speed, because photons are massless. Without mass, there is no restriction on the velocity, which means they can only travel as fast as it is possible to go. Massless particles are the only kinds of particles that can travel at that speed, and they must travel at that speed. Otherwise, they would have no energy or momentum. In essence, if they did not travel at the maximum speed,
Science fiction writers have given us many examples of spaceships traveling through space at the speed of light or even faster. The reality, however, is a bit different. So, is traveling at the speed of light and beyond even theoretically possible?
In Star Trek, they got around this problem because they had warp drives. So if this is like the galaxy, and they're on one side, and they want to get to the other side. And so they turn on the warp engines, and they would bend the fabric of space, because the diameter of the galaxy is 100,000 light years. If you travel as fast as light, it would take you 100,000 years to cross the galaxy. So what they did was they bend space and then take a little bridge across, and then they unbend it back. And that's how they get across the galaxy during the TV commercial. We don't have anything like that. The fastest hunk of hardware we have ever launched, it's going like 4 times the escape velocity from Earth. It's a tiny spacecraft on the largest engines in our arsenal. You combine those two facts, laws of physics say this thing is going to be hauling. If you hitched a ride on that, you would reach the nearest stars in about 35,000 years.
If we look at the Einstein special relativity theory, the speed of light in vacuum has constant velocity of 186,282 miles per second. If you could travel at this speed, you could go around the Earth 7.5 times in 1 second.
If you travel fast enough, you can actually leap forwards in time. Relativity specifies that you travel a good fraction of the speed of light, time will tick more slowly for you than all your loved ones back on Earth. If your journey is too long, you might be gone for 10 years, and everyone else on Earth ages 100. So you've effectively gone into the future, and then everyone you knew when you left Earth is now dead.
Since light travels at finite speeds, when we observe distant objects, we are literally looking into the past. Most of the stars that are visible to the naked eye in the night sky are 10 to 100 light years away. Thus, we see them as they were 10 to 100 years ago. We observe Andromeda, the nearest major spiral galaxy to our own Milky Way galaxy, as it was about 2.5 million years ago. So, if we could travel at the speed of light, it would take us around 2.5 million years to reach Andromeda. The nearest star, Alpha Centauri, is 4.37 light years away. Even NASA's Voyager 1 space probe, traveling at 10 miles per second, which became the first spacecraft to enter interstellar space back in 2012, would take around 70,000 years to get there.
The distance between stars is vast. We would need to understand something new about the fabric of the space-time continuum and exploit that in order to expect to travel to the stars.
So, of course, in real life, if we want to be able to live the life of science fiction and travel to other stars, how might we actually do it? Old school science fiction is you have a rocket ship. Could you build a rocket ship and use it to travel to another star? So the short answer is not really. The way the space shuttle worked is it's full of fuel, and you light that fuel, and you get a massive explosion. You direct the explosion out the back, and the gas flows out that way, and you get a reaction. If you push the gas out that way, you go that way. Okay, so it's very simple, brute force technology, and it pushes the space shuttle up into space. And that you needed all this incredible fuel just to get 300 kilometers above the Earth's surface. So you still haven't even escaped from the Earth's gravity, let alone escape the sun, let alone travel to another star. So even if you could build a rocket that had everything you needed on it to travel to another star, and you built the fastest rocket that's ever been built, it would take about 20,000 years to get even to the nearest star.
If travel to distant stars within an individual's lifetime is going to be possible, a means of faster-than-light propulsion will have to be found. In 1994, Miguel Alcubierre proposed a method that would take us beyond the speed of light limit. In his mathematical theory, he used 2 points in space-time to demonstrate the expansion and contraction of space fabric. The idea of Alcubierre's theory is that we could use this space-time warp to make an object travel faster than light. This theory is also known as Alcubierre drive. Shift space around an object so that the object would arrive at its destination more quickly than light would in normal space without breaking any physical laws. Instead of going faster than light, the spaceship would remain stationary at a time in which the space in front of it is moving faster than light. The ship would effectively ride this supersonic wave to get to its destination without exceeding the speed of light. It was postulated that this warp drive would require a negative energy or exotic matter, thus making it practically impossible to achieve under the current laws of energy and thermodynamics. The other problem with this theory is that the space-time warp would damage any planets or stars it passed near. The energy released by the warp drive could be strong enough to rip nearby planets apart, or even trigger the formation of a black hole at its destination. In March of 2021, Dr. Eric Lenz, a researcher at Germany's University of Gothenburg, published a paper where he showed the existing research and claims to have discovered gaps in previous warp drive studies. Lenz noticed that there existed yet-to-be-explored configurations of space-time curvature organized into so-called solitons that have the potential to solve the puzzle while being physically viable. He believes to have found a way to permit super-fast travel by creating a series of solitons that can provide the basis for a powerful propulsion system. These solitons, in theory, could maintain their shape and move at constant velocity, using sources with only positive energies that can enable travel at any speed. Several other attempts and hypotheses have been proposed in the past to explain the long-standing problem of faster-than-light travel. Einstein's theory of special relativity states that energy and mass are interchangeable, and speed of light travel is impossible for material objects that, unlike photons, have non-zero rest mass. In 1935, Einstein and his colleague Nathan Rosen proposed a hypothetical wormhole theory in which 2 separate points in spacetime are bridged together. In essence, this would form a tunnel or shortcut through spacetime. Einstein's theory of general relativity mathematically predicts the existence of wormholes, but none have been discovered to date. Even if a wormhole could form, it would most likely be very unstable. Wormholes are still speculative, and nobody really knows if you could pass through it. The math suggests that you need some sort of exotic material to pry the throat of the wormhole opening so that it won't collapse on itself. Even then, it is possibly unstable. For a simplified notion of a wormhole, imagine taking a strip of paper and folding it over. You have created a tube-like shape. Now imagine this tube allows for 2 points in space that are far apart to connect together in some way. This is how a wormhole could theoretically work. In a new theory, physicists at the University of Oldenburg have shown that microscopic, traversable wormholes could exist without having to rely on exotic matter or a new theory of gravity. Their model permits the existence of a wormhole traversable by matter, provided that the ratio between the electric charge and the mass of the wormhole exceeds a certain limit. However, this type of wormhole, as postulated by the researchers, would probably not be suitable.
Hi everyone, David Peck, racing event B, and I'm drawing the coordinate system for a rapidly moving observer that is moving at roughly half the speed of light. So after a little bit of struggling with the drawing software, here's the coordinate system. The time-like axis corresponds to the motion of a sublight starship. The other axis corresponds to the space-like axis for our starship. This axis represents all the events that take place simultaneously at the present time for the starship. Now, if we take the space-like axis and shift it down a little bit, then we get a set of points that are all also simultaneous for the starship, but they happen in the past. Now you might notice that I on purpose drew the present and the past space-like axis. Observer, this sounds okay. Event A precedes event C. The only issue is the signal from A to C travels faster than light. On the other hand, what happens for the moving observer? That is the one with the black axis. Well, for that observer, the tachyon is emitted in the present. Out that the theory of quantum gravity, which scientists are currently trying to construct, has something to say about wormholes. Now, a wormhole can be thought of as a shortcut through space.
All right, did everyone have a nice break? So this chapter inevitably breeds questions like science fiction types questions about faster than light travel and communication. You just can't avoid it. So let's embrace it.
Hi everyone, David Pecker here, and in this lecture we are going to discuss tachyons, faster than light travel, and the breakdown of causality. Before getting started arguing about faster than light travel, let's go ahead and define causality. What does causality say? If event A causes event B to
I forgot to turn on the audio. There we go.
Hi everyone, David Pecker here, and in this lecture we are going to discuss tachyons, faster than light travel, and the breakdown of causality. Before getting started arguing about faster than light travel, let's go ahead and define causality. What does causality say? If event A causes event B to happen for one observer, then the same is true for all other observers. That is, all observers can agree on which event precedes which other event and thus causes it. At this point you might say, but what about the breakdown of simultaneity? Well, let's take a look. We start by drawing a space-time diagram with space on the horizontal axis and time on the vertical axis. Suppose that event A occurs at the origin of the space-time diagram. Now, if we were to draw the trajectories of light that are emitted by event A, they would correspond to these two 45-degree lines emanating from point A. This pair of purple lines is called the light cone. The reason why it's called a cone is because if we were to draw this in 3D space, it would look like a 3D cone. Now, any event that happens inside the light cone.
So just briefly, we draw these cones like this because inside those two lines are points in space that could possibly have seen event A, given the fact that they can only find out about A at the speed of light. So if you are 1 light second away from event A, you have to wait at least a full second for that information to reach you. That's the idea that he's presenting here.
Such as event B knows about the occurrence of event A. Therefore, all events happening inside the light cone have causal relationship to event A. This causal relation is true not just for the stationary observer we drew here, it's true for any moving observer as well, because at best we would squeeze the coordinate axis towards one of the branches of the light cone, and the causal relationship would not be able to change. Now let's consider event C, which lies outside the light cone of event A. Event C is not causally connected to event A. The reason for this disconnect is because information traveling even at the speed of light from A could never reach C. The only way information about A could possibly reach C is if it travels faster than the speed of light. So what we're going to do now is think about the consequences. Let me go ahead and declutter the picture by erasing event B and then drawing the coordinate system for a rapidly moving observer that is moving at roughly half the speed of light. So after a little bit of struggling with the drawing software, here's the coordinate system. The time-like axis corresponds to the motion of a sublight starship. The other axis corresponds to the space-like axis for our starship. This axis represents all the events that take place simultaneously at the present time for the starship. Now, if we take the space-like axis and shift it down a little bit, then we get a set of points that are all also simultaneous for the starship, but they happen in the past. Now you might notice that I on purpose drew the present and the past space-like axis for the starship, so that the present axis goes through event A, while the past axis goes through event C.
So this is a typical way of talking about things that happen at different times. So as we just finished discussing, if you are moving fast, you disagree on how long things take in time, and you disagree on how long things are in space. So anything on this black line, for example, every event on this line that happened, at certain distances from the ship and certain times ago from the ship, they all look like they happened at the same time because the light from all of those events reached this spaceship at the same time, right? So at the same moment, light from every event on this black line reached the ship, and so the ship cannot tell the difference, between anything on this line happening before or after.
Now for the stationary observer, that is the one with the pink axis, event A precedes event C. And we can see this because event C is above event A. We can see this explicitly by noting that the space-like axis is a set of simultaneously occurring points that happen in the present, and by shifting the space-like axis upwards, we get the purple axis, which is a set of simultaneous points that happened in the future for the pink observer. Now, what about the observer on the starship, the one with the black axis? Well, for this observer, event C happens in the past, while event A happens in the present, and therefore C precedes A. Consequently, if there was a causal relation between A and C due to faster than light travel, our two observers would be unable to agree whether A caused C or C caused A. For the sake of argument, suppose that faster than light communication is possible, and as event A happens, the people at A emit a faster than light beam towards C, causing event C to occur. Now for the pink observer, that is the stationary observer, this sounds okay. Event A precedes event C. The only issue is the signal from A to C travels faster than light. On the other hand, what happens for the moving observer, that is the one with the black axis? Well, for that observer, the tachyon is emitted in the present and arrives in the past. The tachyon is moving backwards in time. That does not sound so okay anymore. From this discussion, you observe that faster than light travel or communication is synonymous with time travel. Now,
Okay, that's the portion of this that I wanted to share. So yeah, so one of the comments that comes up literally every time I've ever discussed this chapter with students is, what if, blank, some sci-fi reason why we can have some sort of information move faster than the speed of light. If that were possible, right? A tachyon is a fake particle that's used in science fiction a lot to justify things that don't make sense. So tachyons don't actually exist. They're just, but they fill in a lot of plot holes in Star Trek. So if you can communicate about events faster than light, then you have observers moving at different speeds that disagree on which event happened first and which event caused the second event. So in this example of this video that we just watched, so if someone at point A calls someone at point C and causes an event, the person who's actually moving slower than light doesn't know about their faster than light communication, and instead they observe that event C happens before the person at A placed their faster than light call, and so they instead of seeing someone at A pick up the phone and cause the event at C, they observe the event at C and conclude that that is the reason that the person at A picked up the phone. It's problematic. Martin asks, what about entanglement? It's a great question. As far as we know, you can't use entanglement to actually send information. So this is a typical argument for why nothing faster than light
here is a crazy part.
Can exist.
Faster than light travel.
Okay. Of course, that's not the focus of what we're doing today, but since I knew someone would ask, I wanted to share. So what we actually want to do is we want to talk about how this disagreement between observers on time and length gets complicated when we try to add velocity vectors, when we try to calculate momentum, when we try to calculate kinetic energy. For classical situations, which just means, situations that aren't happening too fast and aren't too small. So here's an example from the textbook. If we have a parent pulling a little girl on a sled at a speed of 1 meter a second, and the little girl throws this snowball at a speed of 1.5 meters per second to the left, if we want to add those velocities, it's no problem. We just say, 1 minus 1.5 equals 0.5, and we conclude that that is actually the absolute speed of the snowball. Bam, no problem. But if things are moving fast, then it becomes a bit of a problem. If things are moving fast, right? And so what you should say that it's always correct to use the relativistic form here, right? So if we have two velocities, v1 and v2, their sum is going to be v1 plus v2 divided by 1 plus v1 times v2 over c squared. If v1 and v2 are small, then this whole denominator thing, this second term in the denominator is approximately 0. It's real small. So it's approximately 0, and so the whole denominator is approximately 1. And so if we want to add two velocities, we can just add them, like we learned to last semester. And we will be approximately correct. So for example, in this case with the snowballs, right, this is going to be 1 minus 1.5 divided by 1 plus 1 times negative 1.5 divided by 3 times 10 to the 8 squared. Right. So when we do this, we get negative 0.5 in the numerator, and in the denominator, we get 1 minus 1 over 2 times 10 to the 16. So that's real small. So that's going to be in the denominator 0.99999. See, it's 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There we go. That's what we get. That's a lot of nines. And you may recognize that denominator as very, very close to 1. And so when we are dealing with normal everyday situations, it's okay to just call that 1 and say, you know what, we're good with 14 decimal points of accuracy. That's perfectly fine. Don't even sweat that 16th decimal points. But if we are dealing with things that are fast, then we have a little bit of an issue. So let's do this again with V1 equals 10,000 meters per second, and V2 equals negative 30,000 meters per second. So now if we want 1 plus v1 v2 over c squared, that's going to be 1 plus 3 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Boop, boop. Oh, should be a minus sign because they have opposite signs. There we go. So, you know, it's still pretty close to 1, but we're getting closer to relevant. Right? These 10,000 and 30,000 numbers, these are closer to how things move, like the orbital speeds, right? So satellites and space shuttles and whatnot move at somewhere around these velocities. Right, but the larger the velocities get, the more relevant this factor becomes, and in fact, as you increase your speeds past around 10,000, they get relevant much faster. So, questions or comments? Astute observers will realize that this thing down here, this looks a lot like gamma squared. And indeed it does. This gamma factor plays a huge role in analyzing relativistic motion. Are people still awake? Have we achieved brain mush? So we are almost to the end, right? This gamma factor it's everything. Right? So in classical mechanics, like slow physics, as I like to call it, our momentum is just mass times velocity. In fast physics, right, relativistic, our momentum is equal to gamma. Wow. You know what? I have the hardest time drawing gammas. Right, where again, gamma is square root of 1 minus v squared over c squared. And the last thing we want to handle is energy. Can you guess by what factor relativistic energy differs from classical energy? You're a funny man, Anthony. That's very funny. You all are probably familiar with writing kinetic energy as 1/2 mv squared. And that is correct, but normally, so once we get past, intro physics, we actually write it in terms of the moment of an object. So p squared divided by 2m. Right. Your book plays a game that I don't necessarily enjoy with this, but the total energy, the correct way to write the total energy, relativistic terms, is p squared c squared plus m squared c to the fourth. And some of this derivation is in your book. It has to do, as I'm sure you've guessed, with a factor of gamma that comes up when you convert classical kinetic energy to relativistic kinetic energy. And notably, if p is 0, right? If you have an object that is not moving, then you just end up with the good old E equals mc squared. Non-movement is an assumption. I don't understand necessarily what that means. Can you explain your question?
I just like the way I was thinking about when I was reading the chapter was just it was stating that like everything is moving, like the Earth is constantly moving, so we're just making like an assumption that everything is quote unquote not moving in order to have a the relative version of it.
Yeah, so not that we're assuming it isn't moving, we are defining it to not be moving.
Okay.
So remember, we're allowed to define a reference frame with whatever velocity we like. So this is just like putting your coordinate system right on the front of the train as it's moving. So if we define a coordinate system so that it's moving with whatever we're looking at, then it has no momentum, and all of its energy is what we would call rest energy.
Okay, I see.
Right? So the amount of energy we perceive an object to have does actually depend on how we define our coordinate axes. I think I have mentioned before that there are two ways of trying to understand physics. And the first way is conceptual. Right? Where we ask questions like, what the heck? Why in the world? And how? Seriously, how? And there's definitely like grappling with the questions in this way is definitely worthwhile, especially when we start moving into a description of something that maybe doesn't match our everyday intuition, just because it's trying to describe something that's pretty far from our everyday experience. For this chapter, this conceptual bit is difficult, right? Trying to wrap your mind around how things are different just because of they're traveling fast or slow it's hard to develop an intuition for that, and it's hard to answer the conceptual questions. But there is a second way of understanding physics. And it is the shut up and calculate method. And for relativity, for special relativity at least, for the shut up and calculate method of understanding what's going on, the gamma factor fixes everything. Just slap a gamma on. You've probably got it. I would venture to say that most people who study physics want to be a conceptual person. And even people that end up becoming physicists, they normally succeed right up until the point where they start seriously studying quantum mechanics. And then at that point, you have to just be a SUAC. Because the conceptual interpretation maybe doesn't even exist. We don't have a satisfying explanation for why things happen the way they do at the quantum level. So just run the calculations and design a new cell phone. It's not a big deal. If you spend a few decades studying a particular field, I have heard rumors that you can go from SUAC back to being conceptual. I will let you know if I get there.
Is there any time where you want to be conceptual and you say no?
Yes, for sure. There are astronomers who spend I go to a fair number of talks from my colleagues at UNLV, and astronomers, they deal not just with special relativity like we talked about here, but with general relativity. And I will admit I do not have a conceptual handle on general relativity at all. I can see the formulas, I can do some plug and chug, but it isn't my field. I know it exists. I wish I understood it. I don't. I know just enough to follow along to their talks.
Okay, I was gonna try to ask if you could explain this astrophysics question. It might deviate a little bit, but it's just basically I was just doing a little bit of just watching, and it was talking about how astrophysics, there's many different equations depending on what they're calculating, and none of them really agree with each other on how old the universe is in terms of physical equations, and so nobody really knows for sure how old the universe is.
I think that might have been true 30 years ago. But now, there have been, to excuse the pun, but astronomical leaps in terms of our modeling of cosmology. So, age of the universe is something we actually have a pretty good handle on now.
Oh, okay. Maybe just an older video then.
So that's the sort of and this is where you have to be careful, right? Because there is a lot of popular science that tries to explain things at a conceptual level to people who aren't even at a SUAC level, right? Now, when you did Gen Phys 1, it was sometimes easier to do conceptual as opposed to SUAC. But once you start studying anything that's even a little bit more difficult, the conceptual part is by far the hardest bit. And SUAC becomes much easier. So when you are, there's a lot of science media written by people who can't SUAC for people who can't SUAC. And that kind of media is usually trying to sell something. So be careful of that. Did that answer your question at all?
Yes, completely, actually.
Okay. All right. So that is actually all that I've got for today. So if you are interested in sticking around to chat about whatever, feel free. Next week's quiz will be a SUAC quiz. So, which is fortunate because the actual equations for this chapter are not super difficult. But I won't ask you to conceptually explain something.
So on that same topic, for next week, are we just coming to class to take a quiz and then we leave? Or how
sorry,
is that gonna...
I meant 2 weeks.
Oh, okay.
In 2 weeks. Next week we are not meeting. Nevada Day means that we all have a holiday. So, catch up on sleep, catch up on studying, call your family who you haven't spoken to in several weeks because you've been working too hard. So yeah, do all of that stuff. Yeah, go on a date with your wife, absolutely.
I think Arthur had a question on the on your take on the EM drive.
Yeah. So the EM drive is problematic. There were some initial tests that indicated that maybe they were able to get some thrust out of it. Later results, including one from, I want to say it was really late last year or early this year, showed that all of the thrust... Oh, EM stands for electromagnetic. All of the thrust that was shown in the initial tests was actually due not to any real thrust, but by the warping of the actual sensors during heating of the object. And it's important to note that even the original tests which showed that maybe it works, they were only claiming nanonewtons of force. So it's real easy for something that small to be a sensor malfunction, which it turns out that it was. So yeah, so on its face, it seems weird because it appears to violate conservation of momentum and also the second law of thermodynamics. So there are hundreds of charlatans every year who claim to have invented some free energy system And I think originally, when I first heard about the EM drive, I saw it and I was like, well, this falls under the same umbrella as these free energy hucksters. Um, right? So, like, what's more likely? That a law of physics that we have been relying on for, I don't know, hundreds of years is wrong, or that there's a sensor malfunction, right? And it's really more likely that it's a sensor malfunction. And most of the people who were saying, no, it's not a sensor malfunction, it's new physics, were the ones trying to sell it to NASA. So the EM drive is what I consider a bad example of how to deal with results that seem to violate some understanding of physics. There was a study in 2008, I think, by an Italian research group who were studying the movement of neutrinos. And they got a result which seemed to indicate that neutrinos were moving faster than the speed of light. And they were like, wait a minute, that doesn't seem right. So instead of publishing and saying, oh, neutrino study disproves Einstein, instead they dumped all of their raw data to the internet and was like, hey, open field, someone help us understand what went wrong. That's the right way to do science. Taking a tiny anomalous result and trying to sell it to NASA for $1 billion, that's the wrong way to do science. If you think a warp drive will ever be possible, I have no idea, man. I have played, 700 hours of Elite Dangerous over the years, so it would be sweet if there there did end up being something like that, but I don't expect it to be true. Right, we are just now reaching toward the other bodies in our solar system, and I imagine that's where we're going to be stuck for the next 100 generations or so. Yep, too late for tall ships, too early for spaceships. Am I excited for the James Webb Space Telescope? Absolutely. I'm also really excited for Juno, which is a mission that is visiting the moons and asteroids of Jupiter over the next 10 years. Yeah, time to go work the asteroid mines.
So I have a math question.
Okay.
Okay. So, and it kind of goes along with the whole, like, the difference between doing it conceptually or just calculating. And I can solve the problems because I can understand them, but it's slow. And I need to be able to do them fast because they're on the DAT. And so it's timed and I'm running out of time every time because I just like to sit down and solve puzzles and take my time doing them. And then I get only halfway through. Sure. And I get them all right, but I only get half of them. So it's the ones, and we've had them, there have been a lot of them actually in this physics book so far. If this x and whichever factor is increased by 20%, then by what percent does the total increased? And like I can get there eventually, but what I want to be able to do is set it up the way I do, like with a dimensional analysis question, where I just know I know where everything goes super easy. I can do it really fast, and I can just plug it in and do it without having to really think about it.
Yeah, that's actually a really good question. And this leads to one of my favorite mathematical tricks, actually.
Okay, yay.
So
I like it.
So you might ask something like, if v1, if you triple your velocity,
Okay.
then how much have you increased your kinetic energy by, right?
Okay.
And what you want to do is you want to set it up as a ratio. You divide one equation by another equation.
Okay, that's what I was thinking. That probably had to be the answer ultimately, but okay, show me exactly how I'm going to want to set it up, and then.
Right, like so. And then we go cancel, 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 cancel. And we get T1 equals V1 squared over V2 squared times T2. And so if V1 is 3 times T2, and then we plug in.
Okay. Wait, if V1 is 3 times, okay, so we plug in 3V2 for V1.
Yep.
Right, gotcha.
And that cancels. And 3 squared is 9.
Okay. Cool. Okay. That's what I need. I need to practice that a little bit, but yeah, I need like a formula for how to do it so that I'm not constantly reinventing it every time I do it.
Right. Yeah, dividing one equation by another equation, that's how you want to do it.
Okay. Cool. All right. So yay, no class next week because the date is November 2nd. So, well, day before
it's coming
your
up.
thing. Yeah, you're looking forward to no class next week too, huh?
I definitely am. I have so much grading to do.
Yeah. How much prep are you having to do for your dissertation? Or is that?
It is almost all in.
Oh, good.
So.
Cool.
Yeah. I just have to practice actually giving the presentation, which I have to keep to under 45 minutes and yet still cover everything.
So how much of it, I actually didn't end up going to my brother-in-law's when he did his, the rest of my family did. How much of it is just you presenting and how much of it is questions?
It depends on the committee. It can vary wildly. So the tradition for our department is to allow the speaker to present more or less without interruption. And then at the end of the presentation, they ask all the public viewers to leave, and the committee members will grill the presenter for as long as they like.
Oh, interesting. And why do they ask everyone to leave? Because they don't want to embarrass somebody in front of their family and friends?
Yes, that is correct.
Okay, that's fair. that's kind.
Yeah.
Okay. So, do you have people to practice in front of?
I do. A couple people from my research group have volunteered.
Yeah. It's important.
Yeah. Yeah. So.
Cool.
It's going to be good stuff.
All right. Oh, be nice.
Oh, Nicholas asked if there's going to be a quiz review. What do you mean?
Oh, are you going to go over the quiz from today, I guess?
Oh.
What are you asking?
I guess not. Most people are gone. Do we need to go over the quiz? Do you need to, Nicholas? I can do it if you need it, but I think Nicholas is actually gone. Yep. He's not with us anymore. All right.
Professor, I have a question about my quiz from last week.
Okay. I have not graded it yet.
Okay, cool. I just wanted to make sure that you got it because I know it was quite a situation.
Who
Because
who am I
I'm the one
speaking
who,
to? I don't see your name.
this is Mackenzie. Can
Oh,
you see the
Mackenzie.
yeah,
Yeah,
I
I
know
did
I'm
eventually get it.
okay, cool. Just wanted to make sure.
Yeah. Um. Yeah. No worries.
Okay, thank you so much.
You're welcome.
Bye.
Bye. All right. For the rest of you, have a good weekend and enjoy your week off.